Hey everyone, it's Miss Pasega, and today I am sending you to play the Radioactive Dating game. But hey, before I send you off there, what exactly is radioactive dating? Alright? So, I want you to think of radioactive dating mathematically first and conceptually in a moment. Keep in mind that our rate constant, lambda, for any given element is known, and it stays the same over time. The example shown here is the rate constant for carbon-14, whose half-life is 5,730 years. So that means for a given carbon-14 atom, it has a possibility of 1 in 10,000 of decaying in any particular year. Now scientists know this, and that means if you know how active a sample is now, how many carbon-14s are decaying at a time, versus 100% when it was original, then you could solve backwards for time by solving this exponential decay equation. But I'm not going to be mean. Let's go and see how we were going to do this in our lab today. Radioactive dating is the use of the ratio of the parent to daughter elements to determine the age of a sample. Think of it like this. If we were watching a big sample of uranium decay into lead, if we know how many lead and uranium atoms there are, we can figure out where in this process it is. If there's only a few uranium left, we know a lot of time has passed. If there are only a few lead atoms, then we know only a little as time has passed. Radioactive decay is going to take 3 assumptions. It assumes that we know the original number of unstable atoms. Now we do this with uranium and carbon because we know how much uranium occurs naturally on rocks in Earth. And we also know how much carbon-14 exists in any living thing on Earth. We know the original number of unstable atoms. We know the decay rates are constant. Because the half-life isn't affected by any chemical process that we can do to it, the decay rate is constant over time. So as long as we can make sure that the daughter atoms were all produced by radioactive decay and no one's like adding extra lead to this sample in the meantime, then we can figure out how much time has passed. We know how much carbon exists in living things. So if I plant a tree and use this Geiger counter to measure how much radiation is coming off that tree at a given time, we see that it should always have 100%. But once the tree dies, the tree stops uptaking carbon dioxide, so it doesn't get any new carbon. And as the carbon-14 decays, we can figure out how much time has passed. So if we were measuring, I don't know if I can pause it in here, if we were measuring and only saw 50% of the expected amount of carbon-14, then we'd be able to figure out that exactly one half-life, or that 5,700 years, had passed. Similarly with rocks, when you have an erupting volcano, it's erupting, and you get a rock, we can measure how much uranium is supposed to be in the rock. As the rock cools, the amount of uranium changes over time. And since uranium has a much longer half-life than carbon, it takes much, much longer. Notice this billion-year scale over here. So let's send you on your way. You're going to the dating game, and I want you to grab the Geiger counter. Use it, let's say, on one of these items, house. All right, use it on some sort of item. And that one is a cup, maybe carbon. In this case, if you see 88.2% of the available carbon, I would pull this marker over to 88.2. Isn't this nicer than doing that exponential decay equation? And so about 1,026 years have passed. Woo! With this cup. All right, so best of luck to you guys. Make sure to attach that document back to Classroom when you're done. Bye!